Okay, so thank you. Good morning, everyone. So a major theme in this symposium has been the effect of inhomogeneities in the stellar disk on transit spectroscopy. But I want to point out that even if the host star is not active and has a spatially uniform disk, its spectrum is inhomogeneous. It has spectral features. And you can have problems with transit spectroscopy, and those problems can arise as a bias caused by the overlap between stellar and planetary absorption lines. And this is an effect, actually Kyle Shepard and I published this effect several years ago, and I'm reminding you that this effect is important, and it will be especially important in the JWST era. And it arises when the stellar spectrum is modeled and at inadequately low spectral resolving power. If you use a low resolution stellar spectrum to do your analysis of your transit data and to do your retrievals, you will be subject to this bias. Even if you use a high resolution spectrum, and that high resolution spectrum is not perfect, it's not a perfect representation of the star, there will be a bias effect. So the first thing to remind you of is that the overlap between stellar lines and planetary lines and the radiative transfer that occurs in the transit occurs at high spectral resolving power. So high spectral resolving power, what do I mean by that? This table shows the Doppler width in inverse centimeters in wave numbers for various positions in the atmosphere of the star or the planet in the case of the TRAPPIST-1b system. And in the rightmost column shows you the resolving power, the spectral resolving power that corresponds to that Doppler width. So you would have to observe at that spectral resolving power in order to fully resolve the spectrum. And the resolving powers are typically 10 to the 5th. And in most cases, we do not have observations at that spectral resolving power. So we have to model the effect of the radiative transfer at high resolution and then account for our low resolution observations. Here's the spectrum. In this slide is the spectrum of the star in the TRAPPIST-1 system from a Phoenix model. And the top panel shows the full high resolution spectrum. This is from a paper by Husser et al. In 2013. And the full resolution spectrum is shown in gray. And it's convolved down to a low resolution in blue. And if you use the blue resolution spectrum, which would be convenient to do because low resolution spectra are relatively easy to work with, you have to realize that what's really there at high resolution in the transit of the star is the gray spectrum. The lower panel expands just a portion of that near the water absorption band, which has been observed extensively by Hubble near 1.4 microns. You can see the spectrum of this M-dwarf star is predicted to be a forest of absorption lines that are sharp and present at high resolving powers. So this bias effect is easy to understand. So suppose you're in the core, suppose your wavelength is the core of a stellar absorption line. In the core of that line, the star is much fainter than it is in the continuum. If there's a planetary absorption line from the same molecule and it's absorbing at the same wavelength because the planet's orbit is let's say the orbit is circular, so there's no relative radial velocity difference, the planet is absorbing at the same wavelength, well, the star is not emitting very many photons at that wavelength. So in your observations, after convolving to low resolution, you will see relatively low amount of absorption. But because your low resolution stellar spectrum will be smeared out, the stellar spectrum at low resolution will look like it has a lot of photons. So using a low resolution model, you won't account properly for the stellar line core intensity, and you'll think that the planet is absorbing only weakly, and you can get the wrong answer for the abundance of that molecule in the atmosphere of the planet. Here's an example calculation for the TRAPPIST-1b system. The blue spectrum, now this is the spectrum for a clear atmosphere that has a lot of hydrogen in it, so there's a large absorption. If there were a cloudy atmosphere or a higher molecular weight atmosphere, there would still be a bias effect. In fact, in a relative sense, it would be larger. because the bias occurs predominantly in the strongest lines, and in a cloudy atmosphere, only the strongest lines would be detectable above the clouds. So the blue spectrum is the correct calculation using a high resolution model. The spectrum in magenta is the calculated effect using a low resolution stellar model. It's about a 12% absorption. Now this is at the water band at 1.4 microns, and JWST will be observing stronger bands at longer wavelengths, so where this will be a greater effect. And it will also be relatively greater if the planet's atmosphere has a higher molecular weight or if it's cloudy. So this is an effect that really has to be accounted for when we model JWST transit spectroscopy. So to summarize, this resolution link bias occurs when stellar spectra are modeled at inadequate spectral resolution, or your high resolution models are not perfect, so there may still be bias even when we try to avoid it. It's especially prominent for M-dwarf stars because M-dwarf stars have very complex line spectra with many strong lines. It will certainly be present for molecules that exist in both the stellar and the planetary atmosphere. But if you're observing a molecule that is in the planetary atmosphere but is not in the star, there can still be accidental overlap between the planetary spectral lines and the stellar spectral lines. If it's the same molecule in both the star and the planet, then the effect will be that you will, if you don't account for it properly, you will see less absorption than is really there. If it's an accidental overlap, it could go in either direction depending on how the planetary lines coincide to the stellar lines. You could get absorption that seems to be stronger than it is, or seems to be weaker than it is. So to mitigate this effect, we really need to understand the stellar spectra at high resolution much better than we do. If you take a high resolution Phoenix spectrum now and you overplot an observed high resolution spectrum, you will see that they don't really agree very well on a line-to-line basis. Now, of course, one solution would be to just obtain a lot of high resolution observed stellar spectra and use those in the JWST era. But many regions in the infrared spectrum of the star are not very well transmitted by ground-based, by the terrestrial atmosphere. So ground-based spectrometers can't really get you a good high-resolution spectrum, and we don't have any high-resolution spectrometers in space. So we will ultimately have to rely on models to a large extent, and those models are improving, but we need even more improvements. So I'll stop there.
Excellent. Thank you so much, Drake. I have a question while other folks think. Do you have an understanding for how precisely we need to match our model spectra or observed spectra to the truth in order to avoid this effect?
Well, so it's difficult to, I'm not sure what you mean by how precisely, but I would point out that
maybe given a certain size, given the size of the atmospheric features we're actually looking for.
Yeah, well, first of all, you have to, the spectral line in the star that you're modeling has to coincide. You have to get the right wavelength compared to the Doppler width. So that's much better than we're currently doing. If current spectra, lines are off by several line widths in many cases. So we have to do much better.
All right, and a question from the Slido. What minimum resolution model should we be using with our JWST data?
So I think we should use the Phoenix, the Husser models, the high resolution Phoenix models. I think there's no excuse for not using the highest resolving power model that you have from Phoenix, because the models are available and they're the best we have currently. And so we should use those and then convolve down to the observed resolution after you do the radiative transfer process. So Mike Line and I have talked on that point further. It may be possible to just develop a correction scheme, an empirical correction. In other words, do a few high resolution calculations and develop a correction recipe so that all of our modeling would not have to be done at higher resolution.
Speaking as someone who neither observes planetary atmospheres nor models them, is that a pretty computationally heavy calculation if you had to do that every time?
Yeah, I think if you had to do the radiative transfer at high spectral resolution every time, that would be problematic. Currently, Platon does it, but it does take a while. The retrievals, when I do a high resolution retrieval on my laptop with Platon, I put it in a room of my house and I come back a week later.
Excellent. Okay. Time for one last question, which I think is basically so are there avenues for better theoretical models, or are the high resolution, do we really need to start getting high resolution observed spectra in the long term?
So I think the solution would be a combination of both. So high resolution observed spectra, as much as we can get them, in as many spectral regions as we can, and then use those to inform the, so right now the models are based on line lists from quantum chemistry. And the quantum chemistry groups have made vast improvements, but we need to encourage them to continue to make vast improvements. It's possible that we could correct the line lists and add small wavelength corrections that would give better agreement with the observed stellar spectra, but would not be contradictory to the quantum mechanics of the molecule. If you ad hoc shift a few lines in wavelength to get better agreement with the actual stellar observations, that may be acceptable quantum mechanically.
Excellent. Thank you so much.